Hello. Today we're going to look at two infinite series. The first one will be the sum as n goes from 2 to infinity of 1 over the log of n to the log of n. And the other one will be the sum as n goes from 2 to infinity of 1 over log of n to the log of n to the s. And we're going to see, we're just not going to find out the values of these things. We're just going to look for convergence or divergence. Excuse me. Okay, let's look after the first one under letter A. Well, we look at the denominator here, log of n to the log of n. Okay, that can be written as e to the log n times the log of n. Well, e to the log of n is simply n, so we can bring that down, and this will equal n to the log n. Now, the log n is an increasing function, and it'll go to infinity. And doing a little calculation, we will see that the log n is greater than 1.01 for n greater than or equal to 16. Well, this implies that 1 over n to the log n will be less than 1 over n to the 1.01 for n greater than or equal to 16. And that implies 1 over log n to the log n will be less than 1 over n to the 1.01 for n greater than or equal to 16. And therefore, this implies that the sum as n goes from 2 to infinity of 1 over log n to the log n is convergent. And why is that? Well, we use the comparison test with the well-known p series, where p in this case is equal to 1.01. It's well known that for any p greater than 1, the sum of 1 over n to the p will be convergent. All right, let's look at series B. Again, what's that? It's the sum as n goes from 2 to infinity of 1 over log n to the log n to the s. Now, this is much more difficult to see, so let's get into it, shall we? Okay, log n to the log n to the s can be rewritten as e to the log n to the s plus 1. We're just changing the log n to e to the log n, and that'll raise the exponent here by 1. Okay, what we claim is that there exists a capital N greater than 0 such that the log of n is greater than the log of n to the s, where s is any real number. And that'll be true for all n greater than this capital N. Well, clearly, this is true for s less than or equal to 0. If s is 0, this is just 1, and we certainly can find an n, a capital N, where log n is greater than 1. And obviously, if s is less than 0, this thing here goes into the denominator at that point, and clearly we can find a big N such that log of little n is going to be greater than this thing. Very easy to see that. So we'll leave that for now. We're going to use that later. But for now, let's let s be greater than 0. And let's also let y equal to the log of n. And we want to consider the limit as y goes to infinity of log of y to the s over y. Obviously, as y goes to infinity, the log n also goes to infinity, and vice versa. Simply calling log n y makes the writing simpler. Okay, what is this equal to? Well, Remember, s is greater than 0, so the log y to the s will go to infinity. And y, of course, also goes to infinity. So we got infinity over infinity, and we use, of course, L'Hopital's rule, our best friend. So using that rule, this will equal the limit as y goes to infinity of taking the derivative of the top will be s log y to the s minus 1 over y, and the derivative of the bottom is simply 1. Well, here, depending on what s is, well, let's say s is bigger than 1, and we're going to ignore this 1 in the bottom and just consider the numerator here. And we'll have, again, infinity over infinity. So we apply L'Hopital's rule again, and we get the limit as y goes to infinity of s times s minus 1 times the log y of s minus 2 all over y all over 1. And depending on what s is, we keep applying L'Hopital's rule over and over. So we have an equal dot 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 equal the limit as y goes to infinity of s minus 1, s minus 2, dot, 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 times s minus k plus 1, times the log of y to the s minus k, all over y. Now, depending on what s is, well, s is positive, we know, but what positive is it? Depending on what that is, we have two possibilities. Let's look at that. Now, if s is a natural number, this will terminate here. We'll eventually get s minus s, and that'll be a 0, or something to the 0, which will be 1. And what will be left will be the limit as y goes to infinity of s factorial over y, which of course equals 0. That's if the case is s is a natural number. What if it isn't a natural number? Let's just say it's some other positive number. Well, then keep applying L'Hopital. This will eventually get to the limit as y goes to infinity of s minus 1, dot, 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 s minus k plus 1 over y over log of y to the k minus s. And that's the case if k minus 1 is less than s is less than k for some k natural number. In other words, if s is a positive number and s is not a natural number. And then at some point in our L'Hopital rule chain, the log of y will come downstairs to a positive k minus s exponent. And of course, then we have y going to infinity, log y going into infinity in the bottom. Of course, this will be 0 at that point. So, plugging log of n back into y, we can now say that the limit as n goes to infinity of the log n to the s over the log of n is also equal to 0. And in particular, for s is greater than 0, which we were assuming s is greater than 0 in our analysis right here. Well, since this limit exists by the definition of our limits for at infinity, we can say such that if epsilon is less than 1 and greater than 0, any epsilon in that range, there exists a capital N such that the log of n to the s over the log of n is less than epsilon, which of course is less than 1. This is true for all n greater than or equal to our capital N. Well, what does this mean? Well, let's bring the log n up here. That means the log n to the s is less than log of n for all n greater than capital N. Okay, so we have found a finite capital N such that our log n to the s is less than log n for s greater than 0. And up here, we also found that true for s less than or equal to 0. So now we know that it's true for all real s. Therefore, we can say, since it's true for s, and it's true for any real s, it's also true for s plus 1, obviously. So, the log n to the s plus 1 is less than log n for all n greater than, or capital N. Okay, this also means that 1 over e to the log n to the s plus 1 is greater than 1 over n. We're just exponentiating both sides and then taking the reciprocal here. That's true for all n greater than capital N, of course. Well, this further implies rewriting the e to the log n, one of those, back to the log n. This implies 1 over log n to the log n to the s is greater than 1 over n for all n greater than capital N. Therefore, finally, we can say that the sum as n goes from 2 to infinity of 1 over log n to the log n to the s, there should be an n there, is divergent for all s real numbers. Why? Because by the comparison test with the harmonic series, which is simply the p series with p equals 1, which we know is divergent. And that's the end of the video. If you liked it, consider giving it a like. Thank you very much.